2026 A-Level Chemistry Paper 1, questions 11 up to 20. If you are interested in the other question for question 1 for question 10 or question 21 for question 50, then check out the links in the description down below. Now moving on to the first question, question 11 says, to prepare 250 cubic centimeters of 0.005 mole per cube aqueous solution of iron 2 plus ions, a student uses a compound with the formula of FeNH42 SO42.6H2O, which is found in a bottle in the laboratory. Now this compound has the chemical name of iron ammonium sulfate hexahydrate, and fun fact, has the trivial name of Morse salt. However, that is not relevant to us, as all we really care about here is the number of iron atoms in a single molecule of this compound. And looking at the formula, we can see there is a single iron atom. Now due to that, the number of moles of this compound required is equal to the number of moles of iron 2 plus ions in this solution right here. Now given that the question then says, the label on the bottle indicates that the purity of the compound is 80%. Now what that means is, if we take mass m out of the bottle, then only m times 0.8 will actually be this compound right here. Now given that they ask us the mass of the compound required to prepare the solution is which of these answers, and they tell us the molar masses of hydrogen, nitrogen, oxygen, sulfur and iron. Now to start off with this question, let's try and find the molar mass of this compound right here. So if we take capital M, we can see we have one iron atom, two nitrogen atoms, two sulfur atoms, a total of 8 and 12 or 20 hydrogen atoms, and a total of 8 and 6 or 14 oxygen atoms. So therefore, we have 1 times 1 iron atom of 56 plus 2 nitrogen atoms of 14 plus 2 sulfur atoms of 32 plus a total of 20 hydrogen atoms of 20 times 1 plus a total of 14 oxygen atoms, which is going to be 14 times 16. Now multiplying, we can see we have 56 plus 28 plus 64 plus 20 plus 14 times 16, which is equal to 140 plus 60 plus 24, which is 84. So we have 84 plus 140, which is equal to 224. So we have a total of 224 from 14 times 16. So plus 224. Now adding all these together, we can see if we take the 56 rather, plus the 64, we'll get a total of 120. So 120 from that, plus 28 is 148, plus 20 is 168, and then you have 168 plus 224, which is going to be 12, so 2 on the end, and then carry the 1, we have 1 plus 6, which is 7, plus 2, which is 9, and then we have another one, actually we don't have another one's not carried, so we have 1 and 2, which is 3. So therefore the molar mass here is 392. So we have 392 gram per mole as the molar mass of this compound right here. Now according to that, if we then consider the number of moles required, we can see in the solution we have a concentration of 0.005 mole per decimeter cube, and we have volume of 0.25 decimeters cube, i.e. 250 centimeters cube. So the volume here is this much and the concentration is this much. Now according to that, the number of moles of iron 2 plus is equal to 0.25 decimeters cubed times 0.005 moles per decimeter cube. Now according to that, since the number of moles of iron 2 plus and the number of moles of Morse salt are equal, if we multiply these two, what we'll get is the total mass of Morse salt required to make the solution. Now if we multiply, we can see we have 392 times 0.25 or 104 times 0.005, which is equal to 5 divided by 1000. Now multiply, we can see 392 divided by 4 is equal to 98. So we have 98 times 5 divided by 1000, and 98 times 5 is equal to 450 plus 40, which is 490. So here we have 490 divided by 1000, or in SI units 0.49 grams. Now that means we need 0.49 grams of pure Morse salt to make the solution. But what we have here is not pure Morse salt, but instead only 80% weight by weight Morse salt. So therefore, to get the actual value, we have to realize that M times 0.8 is equal to 0.49. And therefore, M is equal to 0.49 grams divided by 0.8. Now, if you simplify this, you will get the answer of 0.6125, which is the answer number 3. And therefore, the correct answer here is answer number 3. Now, moving on to the next question, question number 12 says, which of the following statements is false regarding the oxyanions of chlorine? Now, chlorine has 4 main oxyanions, and they are ClO-, ClO2-, ClO3-, and ClO4-. And they are named hypochlorite, chlorite, chlorate, and perchlorate. Now, given these 4, we need to know their structures and also the oxidation states of chlorine in each of them in order to answer this question. Now, looking at the first one, for hypochlorite, the structure is 1 chlorine, 1 oxygen single bonded with a minus charge on the oxygen, 3 lone pairs on the oxygen, and 3 lone pairs on the chlorine. Now, given this structure, you can see chlorine has a +1 oxidation state. Now, after that, for chlorite, we have 1 chlorine with a double bond to 1 oxygen, a single bond to another oxygen with a minus charge, 2 lone pairs on the chlorine, 2 lone pairs on this oxygen, and 3 lone pairs on this oxygen. And given this structure, the oxidation state of chlorine is +3. Now, after this, for chlorate, we have 1 chlorine with 2 double bonded oxygens like this, 1 lone pair, and a single bonded oxygen with a minus charge like this. And this oxygen has 3 lone pairs, while the other 2 have 2 lone pairs each. So we have this structure right here, and this structure has chlorine with a +5 oxidation state. Now finally, for perchlorate, we have 1 chlorine with 3 double bonded oxygens and a single bonded oxygen which has a minus charge on it, 3 lone pairs on it, and each of the others have 2 lone pairs on each of them. Now in this structure, the oxidation state of chlorine is +7. Now considering that, if you look at the answers, answer number 1 says the Lewis dot dash structure of ClO2-, ClO3-, and ClO4- contain 1, 2, and 3 oxygen chlorine double bonds respectively, which is true. Here we have 2 ClO2, which has 1 double bond, ClO3, which has 2 double bonds, and ClO4, which has 1, 2, 3 chlorine oxygen double bonds. Now moving on to number 2, it says the oxidation numbers of chlorine ClO2-, ClO3-, and ClO4- are +3, +5, and +7 respectively, which is also correct. +3, +5, and +7. Now moving on to next one, question number 3 says ClO2- has an angular shape. Now this is of course correct because here, even though we have 2 atoms connected to chlorine, we have 4 total electron orbits here, in which case we're going to have these 4 orientating themselves tetrahedrally, and without these 2 electron pairs, we can see the others will have to be in an angular shape. So therefore, 3 is also correct. Now moving on to 4 says the structure of the ClO- contains an oxygen chlorine double bond, which is the incorrect statement because here we can see it contains the chlorine oxygen single bond. So therefore, the correct answer here is answer number 4. Now moving on to 5 says the electron pair geometry around chlorine in ClO3- is tetrahedral, and that is also true. We can see we have 1, 2, 3, 4 total repulsion units, and therefore the geometry here for the electrons will be tetrahedral. Next, if you consider question number 13, it says which of the following graphs best represent the variation of entropy of a substance when it changes state as solid to liquid to gas upon heating. Now for this question, we know that entropy is a measure of the disorder or randomness of the particles within the system. According to that, if we consider solids, liquids, and gases, solids have their particles neatly organized and therefore the entropy is low. Liquids have their particles moving around a little bit, so the entropy is a bit higher. But in gas particles, since the motion is almost completely random, gas particles' entropy is much higher than liquid particles' entropy. Now according to that, when we go from solid liquid to gas, the randomness increases and therefore entropy should increase as temperature increases. Now according to that, graphs 1 and 2 are both wrong, since in both of them, as temperature increases, entropy goes down. Now considering the other three, they all look extremely similar. However, there's a small subtle difference that we need to see by looking closely. So if we look closely at these graphs, we can see here in between these two, there is a change of about 1.5 squares. However, for these two, there is a change in the linear region of about 2.5 squares. Now this change is representing the change from solid state to liquid state and liquid state to gaseous state. If we then consider the other two, we can see in this one, in between solid and liquid, there are about 2 squares or 2.5 squares, and between liquid and gas, there are about 1.5 squares again. Now finally, if you consider the last graph, this one has a squares of about, actually, it's about 2 squares. Now I was going to say it's 2.5, but it's about 2 squares. So we'll say here it's about 2 squares, and for liquid and gas, it is also about 2 squares. Now, considering solids and liquids and gases, the entropy change from solid to liquid is a certain amount, but when you go from liquid to gases, the amount of entropy change is higher than that, because gases are much more random than liquids are compared to solids. So due to that, the entropy change from liquid to gas, which is the second bump here, should be larger than the first bump. Now considering the graph, we can see for this one, it is larger. We have 2.5 here and 1.5 for solid liquid. So therefore, answer number 3 could be the correct answer. Now looking at the other two, we can see in graph 4, the liquid gas one is actually less than the solid liquid one. And therefore, graph 4 is incorrect. Similarly, for graph 5, since both of these are approximately equal, it is again incorrect, and therefore the correct answer is answer number 3, because entropy increases as temperature increases, and the difference between solid and liquid is less than the difference between liquid and gas. So with that, we're done with question number 13. Now moving on to question number 14, it says, consider the following equilibrium which exists in a closed rigid container at a given temperature where M is a metal. So here we can see we have metal oxide solid plus hydrogen gas in equilibrium with metal solid and H2O gas. Now given that they say a series of experiments were carried out with different initial concentrations of hydrogen gas while keeping the metal oxide solid in excess. Now given that they ask us which of the following graphs represent the variation of the equilibrium concentration of H2O gas with the initial concentration of hydrogen gas. And here, initial concentration of H2 gas is given by H2 gas concentration initial, and equilibrium concentration of H2O gas is given by H2O gas equilibrium. Now here, since metal oxide is in excess, the only reactant here that's relevant is hydrogen gas. And therefore, as we increase hydrogen gas, we should expect the concentration of H2O gas to also increase. So out of these graphs here we can see the correct graphs are either graph 2 or graph 4, since in the other ones, when we increase H2, the other one decreases or stays the same. So therefore, these three are wrong, and the correct answers are either 2 or 4. Now in 4, at a certain point, the graph flatlines. This means, other than the hydrogen, there is another limiting reagent which is preventing the H2O concentration from going any further. Now this is incorrect because the only other reactant, which is metal oxide, is kept in excess. So due to that, graph number 4 is wrong, and the correct answer here is answer number 2. So with that, the answer to question number 14 is answer number 2. Now moving on to question number 15, it says, consider the reaction scheme given below, and in the reaction scheme, we have two unknown compounds, X and Y. Given that they ask us, in the reaction scheme given above, the structures of X and Y are respectively which of these? Now looking at the reaction scheme, in the first reaction, we have this compound with a double bond here reacting with cold concentrated sulfuric acid. Now in this case, what happened is the double bond's electrons will be pulled towards the hydrogen, resulting in the heterolytic fission of H2SO4 as H plus and HSO4 minus, like this. Now when this happens, the H plus will be bonding towards this carbon right here, creating the compound of CH3, C, CH3, CH3, where the central carbon here will be positively charged. So we have this carbocation as an intermediate being created here. Now when this happens, the HSO4 minus ion will be attracted towards the plus charge and bond with the central carbon here, resulting in the compound of this thing with HSO4 bonded here. Now when we have the HSO4 group, usually we don't write like this, but instead write as O SO2 OH to indicate the actual structure of O SO double bond and OH. So according to that, the structure of the compound X is this structure right here. Now look at the first ones in the answers here. We can see in the first one we have not the correct structure, because here we're supposed to have CO SO2OH, but instead we have directly carbon to sulfur bond. So the oxygen here is missing, and therefore this one is incorrect. Now look at the third one. We can see in this one we have CH3 here, but the carbon on the end here is the one connected to this group here. It's not correct. It should be the central carbon like this. So therefore number 3 is also incorrect. Now moving on to number 5, again we have the same thing, where we have the end carbon here, not the central carbon, being bonded to this group, and here we have another mistake in that here we are missing an oxygen. So therefore this one is also wrong. Now moving on to this one, number 2, we have an incorrect structure, because here we only have 3 carbons, and here also we're missing the oxygen here, which means what happened here is that we're missing oxygen and also one of these CH3s. So therefore this one is also wrong, meaning the correct answer is answer number 4, which is this answer right here. Now in the second step, when we add H plus and H2O with the heat, what's going to happen is this group will go away, and instead of that we'll have an OH group connecting to the carbon here, which means instead of this group right here, we should have OH in the same position which we have over here. So therefore answer number 4 is the correct answer for this question. Now moving on to question number 16, it says 2 rigid containers A and B are connected through a valve as shown below. Initially, container A is filled with an ideal gas while container B is empty, i.e. a vacuum. Now given that they ask us to predict how the entropy and Gibbs free energy system change when the valve is opened, and here they say consider that the temperature does not change. Now if the temperature does not change, then delta H is equal to 0. Now considering that when the valve is opened, since the volume here will increase, and since entropy is proportional to the number of random states that our particles can have, when the valve is opened, since the number of random states the particles can have is increased, we can say entropy must increase. So therefore change of entropy delta S must be positive. Now given that we know that delta G is equal to delta H minus T delta S, and from this we can see delta G is equal to 0 minus T, which is a positive number, times delta S, which is also positive. Now due to that, T times delta S is positive, and therefore minus T delta S is negative, and therefore delta G here is going to be a negative number. So from this we can see delta G is negative and delta S is positive, so therefore entropy increases while Gibbs free energy decreases. Now from that we can see the correct answer is answer number 3. Entropy increases and Gibbs free energy decreases. Next, if we consider question number 17, it says the elementary reaction 2x gas plus y gas turns into Z gas takes place in a closed container at a given temperature. Given that they ask us by what factor would the rate of the reaction increase if the concentration of X gas is doubled and that of Y gas is tripled. Now for this question we know that given an elementary reaction, the rate is proportional to each of the reactant concentrations raised to the power of the coefficient in front of them. So therefore it's proportional to here X gas concentration raised to the power of 2 times Y gas concentration raised to the power of 1. Now according to that we can see if the X gas concentration doubles, a factor of 2 is increased over here, so you have times 2, and if X gas increases by 2, then X gas squared will increase by 2 squared, or 4 times. Now similarly for Y gas, if Y gas is tripled, then we have a factor of 3 on the inside here, and 3 raised to the power of 1 is equal to 3. So therefore the rate increases by 2 squared times 3, i.e. 4 times 3 or 12 times. So therefore the factor at which it increases is 12 times, which is answer number 3. Now moving on to question number 18, it says consider the following reactions, and it gives us 3 reactions along with the respective delta G standard values. Now given that the question asks us to find the value of delta G standard of the reaction, 4 ammonia gas plus 8 O2 gas turns into 4 aqueous nitric acid plus 4H2O liquid in kilojoule per mole. Now to find this value, what we're going to do is to take these three reactions, which I'm going to call reaction number 1, reaction number 2, and reaction number 3, and find the linear combination of these reactions that creates this reaction right here. Now considering that we can see on the left hand side, on the reactants, our reaction has 4 ammonia gas, and in terms of these three reactions, only one of them, reaction number 1, has ammonia gas in it and has 4 ammonia gas as a reactant in it. Now due to that, both of these have 4 ammonia gas as a reactant, and therefore the linear combination for this reaction must have a single unit of reaction 1 in it. So we have 1 unit of reaction 1. Now similarly, if we take a look at the products, we can see we have 4 nitric acid over here, and in terms of nitric acid, these three reactions only have nitric acid over here in reaction number 3, and here it also has 4 nitric acid aqueous on the product side. So therefore, both of these have the same amount of nitric acid, and therefore we must have in the linear combination of this one only a single unit of reaction 3. Now if we just add these two, we can see we'll get the 4 ammonia gas that we want as a reactant, 4NH3, but then we'll get 5H2O, or rather 5O2, and on the reactant side also 4NO2, add another O2, so that's total of 6O2, and 2H2O, giving us 4NO plus 6H2O plus 4HNO3. 4HNO3. Now here, what we want is not this. We don't want these H2Os here. We can cancel them out. If we cancel them, we can see we have 4 H2Os here. But after that, there are still some unnecessary values here because we want only 4HNO3 and 4H2O on the product side and not this other 4NO. So we have to somehow get rid of this 4NO. Now to get rid of this one, what we can do is to take reaction 2 and see what we can do to substitute. So here we can see on this side, we have 4NO gas. So therefore, if 2NO gas, so therefore if we multiply this by 2, we will get 4NO gas on the product side. So therefore, if we multiply this by 2, we will get on the left hand side 4NO2 being equal to 4NO plus 2O2 gas. Now from this we can see, if we subtract from this reaction, the second reaction, this 4NO2 on this side will cancel, and on this side the 4NO will cancel, and over here, when we subtract on the product side, this 2O2 will go to the reactant side and give us 8O2 in total, which is what we want over here. So therefore, what we're going to do here is to do 1 plus 3 minus 2 times 2, and that will give us the reaction that we want, which is 4NH3 plus 8O2 turns into 4HNO3 plus 4H2O. So this is the linear combination that we want. Now according to that, if this total thing has Gibbs free energy change delta G standard, then delta G standard will be equal to the linear combination of the delta G standards of each of these reactions. So therefore, we have a single unit of 1, which is negative 1010, so negative 1010. We have a single unit of 3, which is negative 170, so we have negative 170 for 3, minus 170, and then we have minus the value for reaction 2, which is equal to 70 plus 70 minus plus 70 times 2, which gives us minus 1010 minus 170 minus 140. And simplify, we can see this gives us 1000 here minus 1000, and for the rest of it we have 40 plus 70 plus 10, which is equal to 80 plus 10, or 80 plus 40 rather, which is equal to 120. 120 plus 100 plus 100 is equal to 320. So we get negative 1320. So therefore delta G standard here is negative 1320 kilojoules per mole. Now looking at the answers, we can see the correct answer here is answer number 1, negative 1320 kilojoules per mole. And with that, we're done with question number 18. Next, if we consider question number 19, the question asks us, upon the addition of excess dilute HCl, which of the solid compounds given below gives a clear solution and evolves a gas which turns filter paper soaked with acidified potassium dichromate green color? Now looking at the answers, answer number 1 is immediately incorrect because when zinc bromide reacts with HCl, all we'll get is zinc chloride and no gas created. And therefore, answer number 1 is not the correct answer. Next, if we consider number 5, in number 5, when we react it with HCl, we'll get chromium chloride like this, which is green color, and then we will not get any gas. And therefore, answer number 5 is also incorrect. Now next, if we consider number 3, we have sodium thiosulfate, which when reacted with HCl will produce us sodium chloride, SO2 gas, and sulfur, which is a precipitate. Now here, while SO2 gas does react with this thing right here, the sulfur precipitating means that the solution here is not clear. There is a precipitate. We'll have colloidal sulfur in the solution. And therefore saying it has a clear solution is incorrect, meaning the answer is not answer number 3. So number 3 is also wrong. Next, if we consider number 2, for a similar reason, when we react this thing, silver carbonate, with HCl, we will get silver chloride, which is a white solid precipitate. And therefore, the solution here is also not clear, which means answer number 2 is also incorrect, and by elimination, the correct answer is answer number 4. Now finally, if we move to question number 20, the question says, consider the following reaction. It gives us a reaction and then asks us what the product formed is. Now for this question, all you have to know is that sodium borohydride in methanol is a weak reducing agent and it can reduce CHO as in aldehydes down to their respective alcohols of CH2, OH, and it can reduce ketones like this into the respective alcohols as CH, OHR, but it is not strong enough to reduce carboxyl acids of COH or to reduce ester groups of C double bond O, ORs. Now according to that, in this compound, we have a carboxylic acid group, a ketone group, an aldehyde group, and an ester group. Now out of these two will remain unchanged, but these two will be replaced by the corresponding alcohol groups. Now looking at the answers, we can see in answer number 2, these two groups remain as they are, but the other two groups, the aldehyde group and the ketone group, are replaced by their corresponding alcohols. And therefore the correct answer here is answer number 2. Now with that, we're done with all of the questions from question number 11 up to question number 20. So I hope you enjoyed. If you have any feedback or questions, then post them in the comments down below. Thank you for watching and goodbye.